Okay, so let me say the rules first because there are too many people, and I think this is first serious lecture by Diksha, so we need to make sure that everything works fine. So so unless you have a very pressing question, let's keep the question till the end of the lecture. Or also you can post the question in the chat box, and I will moderate. I will try to find a natural place to stop her and ask the question. Okay, but if it's really pressing, you feel that you cannot proceed anymore unless this question is answered, then please unmute. But yeah, so we have to cooperate a bit. That's roughly the rule for this, and let's see how it goes. And if we need to change it for next future ones, then we will see how it goes. Okay. Am I forgetting anything, Mukta?
No, it's okay. So we can start now.
Okay, so so we are very happy to have Diksha. So Diksha was a student from IISER Pune, not IISER Pune, IISER Mohali, 2011 to 16.
Yes.
Then she went to SISSA and did PhD and with Atish Tabulkar. She just finished. She defended her thesis in November, so just little bit more than a month. So she worked on various things, and one of them is supersymmetric quantum mechanics. And so yeah, let's begin, and yeah, I hope all of you will enjoy it. Okay, so yeah, Diksha, let's try screen sharing, and we will see how it goes.
Yeah. Okay. Hi everyone. Thanks a lot for inviting me for these lectures. Okay, so I'll share the screen, and if there is something wrong, let me know. Like if you cannot see or hear me properly. Okay. Can you see the board? Okay. So I will be talking about supersymmetric quantum mechanics. I have divided my, I have prepared for 5 lectures. And so basically the outline of my lectures is follows. So in the first one, it will be very pedagogical. I think everyone will be able to follow. And please let me know later on if I was too slow or too fast so that I can gauge my speed. So in the first lecture, I'll talk about why supersymmetry is important. And then I will go on to describe a fermionic harmonic oscillator, then a supersymmetric harmonic oscillator. Then in the second lecture, I will cover supersymmetric Hamiltonian systems. And then I will try to, so I will tell you how Suzie is useful in solving problems. So more precisely, I'll solve hydrogen atom using that. And then I will also talk about Witten index and Suzie breaking. Okay. So before proceeding, let me give you some references. So for the Hamiltonian formalism, so I'll mostly be working in Hamiltonian formalism. One of the good references is this. So archive 9405029. The name is Supersymmetry and Quantum Mechanics. It's by Fred Cooper and Avinash Khare. And the second reference is for Lagrangian formalism. And it's a book called Mirror Symmetry. It's a very good book actually. And chapter 10 of this book as supersymmetric quantum mechanics. Okay, so let's begin. So the first thing is why. So what is supersymmetry? So as you guys know, that we classify particles on the basis of how they behave when we have bunch of the particles. So on the basis of statistics, we classify. So we classify particles on the basis of statistics, and the classification is as follows. We have particles called bosons. You must have heard of it. Then we have something called fermions, and then we have something called anyons. But these occur only in 2D, and I will not cover those in the lectures. So okay, so I'll start just from very basics. Let me tell you what are bosons. So bosons are something which, one of the main properties of bosons is if you have a bunch of bosons, they can sit in the same quantum state. So there is no limit on how many bosons can sit in a quantum state. And more precisely, they follow Bose-Einstein statistics. That is expectation value of the number of bosons. So number of bosons at energy EI. This is given by GI over exponential EI over KBT minus 1, where this GI is the degeneracy. So if at a certain energy level there are that energy level has a degeneracy 2, that will come here, and EI is the energy, KB is the Boltzmann constant, T is the temperature. So at a given temperature, if you want to know what is the occupation number of bosons in a particular energy level, it's given by this Bose-Einstein statistics. You must have seen this in your statistical mechanics course. The other property of boson is that if you have two bosonic wave functions, let me call them psi boson 1 and psi boson 2. If you have two bosonic wave functions, and if you interchange these two particles, so if you interchange them, you just get psi boson 2, psi boson 1. There is no sign here. It's just, if you interchange two bosons, you get the same state basically. So this is a key properties of boson. Another property of boson is that they have integer spin. So you can have spin 0, spin 1, up to so on. Spin 2. And you must have seen examples of bosons. So some of the examples are, you have photon, which is a boson, and you have protons, and you have other particles. You must have seen examples of bosons. So these are bosons. Now the second type of particles are fermions. So what is the definition of fermion? So if on the basis of statistics, that is, if you have a bunch of fermions, how they behave is following. So they obey Pauli exclusion principle. That's one of the defining properties of fermions. So what is Pauli exclusion principle? That is, no two fermions can sit in same quantum state. So as you know, electron is a fermion. So if you remember hydrogen atom, no two fermions can sit in the same energy state. If one is spin up at energy level E, the other one has to be spin down. So there are like different quantum numbers. All the fermions should take different quantum numbers. Second is they obey Fermi-Dirac statistics. So Fermi-Dirac statistics is basically the expectation, the occupation number of a fermion at energy EI is given by 1 over exponential EI kBT plus 1. Notice there is no degeneracy because, as I already told, no degeneracy, and the difference here is there is a plus sign here for the boson. There was a minus sign here. So third, under interchanging, if you have fermionic wave function psi f1 and another fermionic wave function psi f2, and if you interchange these two, you get a minus sign, psi f2, psi f1. So you get a minus sign if you interchange two fermions. This is a very crucial property. Next thing is they have half integer spin. So it's basically spin half, spin 3 half, and so on. So examples. One of the example you must know is electron is a fermion. Okay, so this was very basic. So now I'll define what is supersymmetry. So supersymmetry is a symmetry between fermions and bosons. So it's a symmetry between fermions and bosons. Basically, if you have a supersymmetry generator Q, it's called supercharge. If it acts on a boson, so if it acts on a bosonic state, it gives you a fermionic state. So there is a symmetry between bosons and fermions, and by applying the symmetry generator, you go from a boson to a fermion. That's the supersymmetry. And usually, if you read literature, you will find notation like n is equals to 1 supersymmetry or n is equals to 2 supersymmetry. What does this mean? This basically n is equals to 1 basically means there is one supercharge. Notice that this supercharge, it has taken the thing with integer spin to half, something with half integer spin. So this means that this Q has spin half. So Q has a half integer spin. So if Q has a half integer spin, this implies Q is a fermionic generator. So till now, most of the symmetry generators that you know, so you know the symmetry generator, for example, for translation, momentum is the symmetry generator. That symmetry generator is bosonic. Most of the symmetry generators that you might be familiar with are bosonic in nature. But this one, supersymmetry generator, is a fermionic generator. This will come to play an important role when we discuss supersymmetry algebra. So, and now for the fermion, the number of components of a fermion depends on the dimension. So, for example, let me, if you have a dark fermion, so how many independent component a Dirac fermion will have? If you have seen the Dirac equation d slash psi is equals to 0, it's a zero energy equation. If you have seen a Dirac equation, you know that the psi is has 4 components in 4D, and depending on the dimension, the number of components of a fermion change. So whenever you read a literature and you see n is equals to 1 supersymmetry, you also need to know what is the dimension, in which dimension they are talking about. So given the number of dimensions D and what supersymmetry, it tells you how many independent supercharges you have. So you can have, if it's n is equal to 2, it means you have more supercharges, so you have more number of supersymmetry generators. If you have only one supersymmetry generator, it's n equal to 1. And so whenever you have to count how many supersymmetry generators are there in your system, you need to know the dimension of the system, and you need to know what is it n equal to 1 Suzie or n is equal to 2 Suzie. Okay. Now, also this symmetry is a space-time symmetry. So what I mean by space-time symmetry is that it acts on coordinates. So for example, what are the other examples of space-time symmetries you know? For, let's say translation. Translation is a space-time symmetry. How translation is a space-time symmetry? Because it takes x to some x plus a. So it acts on the coordinates. But on the other hand, if I take a gauge symmetry, this is not a space-time symmetry. Why? Because it acts on the field, on the gauge field, and it takes gauge field to some other value. Similarly, supersymmetry is a space-time symmetry. So it acts on the coordinates. Okay. So let me now go to why we need Suzie. Why supersymmetry is introduced. So one of the main reasons, I will be only talking about quantum mechanics, but if I see from a quantum field theory perspective, one of the main reasons for introducing supersymmetry is Coleman-Mandulla theorem. So this theorem is a no-go theorem. This what it says, that if you have a quantum field theory and you want the S matrix, so you want the scattering matrix of this quantum field theory to have certain nice properties. These nice properties are basically, you want it to be local, you want causality. Okay, don't worry if you don't know these things. I'm just telling this for the sake of completion. Since I will be talking only about quantum mechanics, you will not need most of these things. I'm just stating those for the people who are more interested in why even we have introduced supersymmetry, why is supersymmetry required. So the Coleman-Mandulla theorem basically says, if you have a quantum field theory and you want the S matrix of that quantum field theory to have nice properties as locality, causality, unitarity and all, under these assumptions, the only possible symmetries of S matrix are the following. So you can have Poincare symmetry. So what is Poincare symmetry? Poincare symmetry is translations plus Lorentz symmetry. This has rotations and boosts. And other thing is you can have internal symmetries. So the maximum space-time symmetry. So Poincare is a space-time symmetry because it acts on coordinates. So the maximum space-time symmetry that you can have is a Poincare symmetry. And other symmetries that you can have in your system are internal symmetries like the gauge symmetry or a global symmetry. So this is a very restrictive statement telling you what all you can have, what symmetries a quantum field theory can have. But then when they proved this theorem, they assumed that all the symmetry generators are bosonic generators. But if you extend their argument to include, if you include fermionic generators, in that case the maximum possible symmetry, maximum allowed symmetry under all these assumptions of S matrix, that it has to be local, causal, unitary and all, the maximum, then there is positive energy condition also you have to apply. So maximum allowed space-time symmetry is Poincare plus supersymmetry. and then
Diksha, there is a question. The question
Yes.
says that what does it mean to say momentum operator is bosonic?
It basically means that it doesn't change the spin of the particle. So it has spin 0. So spin 0, that means integer spin things are basically your bosonic, are bosonic in nature. Is it okay? And there's another thing also, which is basically when a symmetry, which I will explain in a moment, is when a symmetry generator acts with a commutator, it's usually bosonic. When it acts like a anti-commutator, which I will introduce, it's fermionic. As you will see, the supersymmetry generators, they act as a commutator, anti-commutators. But for now, you can just think of that momentum generator doesn't change the spin of the particle. So it has spin 0, so which is basically in a sense that it's bosonic. Okay. So if you include fermionic generators as well, then the maximum allowed symmetries, space-time symmetries, are Poincare and supersymmetry, and then you can have internal symmetry. So this is the maximum thing you can have. So this is one of the rules in physics. If it's not ruled out and if it's allowed, it should be there. So this is one of the main, at least I find this one of the main motivations of introducing supersymmetry, that this is the maximum allowed space-time symmetry that you can have if you assume that your S matrix has all these properties. Then there are other reasons also for introducing supersymmetry. So the second reason is basically it solves naturalness problem. I'm not sure if you guys know about this problem. Basically, when you are working with standard model, the Higgs mass, when you compute loop corrections to the Higgs mass, it has divergences, and supersymmetry helps you to remove those divergences. Don't worry if you don't know it. I'm just telling you one of the reasons why it was introduced. Then another reason why it's nice is that it makes computations simple. As you will see in coming lectures, it makes so the computation of hydrogen atom, it's very difficult computation. You introduce spinor harmonics, you then compute energy levels and all. By introducing supersymmetry, by using supersymmetry techniques, you make computations easier. And there is some very nice technique in supersymmetry called localization, which I don't think I will have time to talk about it. Using this technique, you can basically exactly solve for partition functions for some of the supersymmetric partition functions. And once you know partition function of a system, you know everything about the system. You can compute everything if you know partition function. So it's a very powerful tool to make computations easier. Now, so most of these motivations are quantum field theory motivations, but you can understand a lot of the features of supersymmetry just by working with quantum mechanics. So you do not have to go into the complications of quantum field theory to understand how supersymmetry is useful. You can just understand it in quantum mechanics. So that's why in our lectures we'll focus on supersymmetric quantum mechanics, so that you do not get lost into the details of a quantum field theory system. Okay. So since I want to talk about supersymmetric harmonic oscillator, it's a good idea to first review bosonic harmonic oscillator. This I think most of you know.
So Diksha,
yeah?
Maybe this is a natural point to stop and ask if somebody has some question, and then we proceed on.
Yeah. So any questions?
Yeah, if any of you have some very pressing question which you cannot keep till end, you can ask now. Otherwise, we will proceed.
You can ask. Okay. Should I then proceed?
Yes.
Okay. 1 second. So this is, I'll first review bosonic harmonic oscillator. So the Hamiltonian of a harmonic oscillator is p square by 2. P is momentum plus x square by 2. So I have taken the spring constant k and I have taken the mass, everything to be 1, just so that I don't have to write a lot of things. So the Hamiltonian is this. And now, as you do in in the harmonic oscillator, you define the creation and annihilation operator. So you define the annihilation operator A as P minus Ix, and then A dagger as 1 by square root of T, P plus Ix. Now, you know, in quantum mechanics, we have the commutation relation between X and P, which is I have taken H cross again to be 1. So I'm putting most of the constants to be 1 so that I don't have to write a lot of things. So using this commutation relation, you can find the commutation relation. So what is a commutator? Commutator is basically XP minus PX. Okay, these are the operators. This is I. Now, using this, you can find the commutator relations between A dagger. So what you have, A commutator is and A dagger commutator. Both of them are 0. A dagger. Let me just check so A dagger is basically 1. And now using this A and A dagger, you can write the Hamiltonian as A dagger A plus half. This is also called number operator N. Okay. And now you can find the commutators of Hamiltonian with these operators. So H with A, you get minus A, and H with A dagger, you get A dagger. Okay. Now, what's the ground state of the system? So ground state. So the ground state is defined as the state which is annihilated by the annihilation operator A. So A acting on 0 is 0. And if you now want to know the energy of the ground state, H acting on 0 will give you half of 0. So the ground state energy of the ground state is half. And now one can create the Fock space. Fock space is what are the states in your system. So it's the Fock space can be created by acting on the creation operator. So A dagger operator. You act A dagger operator on your ground state. So A dagger on 0 is the one state. A dagger square on 0 is 2 state. So n particle state is basically given by A dagger power n whole square root of n acting on 0. Since it's a bosonic harmonic oscillator, there is no limit on the number of particles you can have in a state. So you can have an n particle state, which is given by this, and you represent it as n. And also you know that if I act, so these are the things we already know. So I'm just writing down the, if you act A dagger on n, you go to one higher state. So you get square root of n plus 1. These normalizations you must have worked out once at least in your life. Square root of n plus 1, n plus 1. So this, because it increases the particle number from n to n plus 1, so it's called raising operator. And A acting on n gives you square root of n minus 1, and it's called lowering operator. Also, A and A dagger increase and decrease the energy by E plus 1. So energy, so if the state psi, so if you have a state psi which has energy E, then the state A psi will have energy E minus 1. This you can work out. And similarly, the state A dagger psi will have energy E plus 1. So it is. Okay. So this I think you guys know very well. So now let me go to, this was just a review. Let me go to fermionic harmonic first. So one of the key features of which defines a fermion is a Pauli exclusion principle. No? So you know, because of Pauli exclusion principle, you can only have two types of states. You can only have either state 0, which has basically no particle, or you can have the state 1, which has one fermionic particle. You cannot have the state 2, which is basically okay, let me call the fermionic creation and annihilation operators as B and B dagger. This is creation of creation operator, this is annihilation. So the state 2, which you should have gotten by applying B dagger square on 0, this should be 0, because you cannot have two fermionic particles sitting in the same state. So because of Pauli exclusion principle, you know that B dagger square should be 0. So but you also know that B dagger itself is not 0. So B dagger acting on 0 should give you 1. So B dagger itself is not 0, but B dagger square is 0. So this you can get by imposing the following rule. So instead of imposing commutators, you impose anti-commutators. So anti-commutator, what is the anti-commutator? So if you have A and B, anti-commutator you represent by these curly brackets. The anti-commutator is given by AB plus BA. So you have a positive sign here instead of a negative sign. So remember, in the commutator you had a negative sign here. In anti-commutator you have a positive sign. So now, since you want this to happen, you put anti-commutator of B dagger is which basically will be B dagger 2 times B dagger square. You want this to be 0. So now for the fermionic harmonic oscillator, the anti-commutator rules are following. If B, the annihilation, B dagger, creation, both give you 0. B dagger, on the other hand, similar to A dagger, is again 1. Here it's, but here instead of commutator, you have anti-commutator. Okay. Notice that this property that the operator itself is not 0, but the square is 0, is a very strange property. It's a property which is obeyed by something called Grassmann numbers. I will not go into details of Grassmann numbers because okay. So what are Grassmann numbers? Grassmann numbers are basically if you have two Grassmann numbers, let's say psi 1 and psi 2. So if you interchange, so they obey this. Psi 1, psi 2 is minus psi 2, psi 1. If for the normal number, let's say if you have 2 into 3, it will be same as 3 into 2. No, there is no negative sign. But for the Grassmann number, there is a negative sign which comes. From here, if you see that if psi 1 is equals to psi 2, this will imply that psi 1 square is 0. This is the property, this is a defining property of a Grassmann number. So fermions are represented by Grassmann numbers. Now you can define the integration rules, the differentiation rules of these Grassmann numbers. I don't think I will be able to talk about path integrals because the integration rules will come there, will come into use there. So I'm not telling you those rules now. If I decide to talk about path integrals, I'll explain more about Grassmann numbers. Any questions? Because I think this is a very new thing which a lot of you might have heard for the first time. Okay, so I will proceed. So till now you have learned that fermions, since they obey Pauli exclusion principle, they are represented by Grassmann numbers. And for the fermionic harmonic oscillator, instead of anti-commutator relations, you have commutator relations, you have anti-commutator relations. And using that, now the Hamiltonian of a fermionic harmonic oscillator is basically B dagger B minus half. Notice that there is a minus half. In the bosonic one, you had a plus half. And this is again called the number operator. And fermion, I'll write. Okay. This one I will call as N boson. Okay. Now, so the Fock space. So what is the, okay, let me first define what is the ground state. So the ground state is a state which is annihilated by the operator B. So B acting on this state 0 gives you 0. So this is the definition of ground state. And then the energy of the ground state, HF acting on 0, will give you minus half times 0. So the ground state has a negative energy. Now let me consider the Fock space of this Hamiltonian. The Fock space only has two states. One is the ground state 0, and the other state is the B dagger operator acting on 0. This I call the state 1. Notice that there is no other state because B dagger square or B dagger power n acting on 0 will give you 0 if n is greater than 1. So there are only two states in the system. And the energy of the B dagger 0 state, so the Hamiltonian acting on state 1, this I think you can compute, which is basically Hamiltonian acting on B dagger 0, HF. This is, I give you as a homework. This you can check. This is half. So the energy is half. So try to just work it out. Okay. So try to find the energy. Okay. Now let's go to the supersymmetric harmonic oscillator. Any questions till now? Okay. So supersymmetric harmonic oscillator is basically a combination of the above two systems. So it's a combination of fermionic and bosonic harmonic oscillator. And I assume for the simplest case that there is no interaction between them. So since there is no interaction between them, this basically means that the fermionic creation and annihilation operators, so fermionic operators which are your B and B dagger, and your bosonic operators which are A and A dagger, all of these commute with each other. So because I am assuming that there is no interaction between those two. So the supersymmetric harmonic oscillator, the full Hamiltonian of the system is Hamiltonian of the bosonic harmonic oscillator plus Hamiltonian of the fermionic harmonic oscillator, which is basically A dagger A plus half plus B dagger B minus half. This half cancels. So you have the Hamiltonian is A dagger A plus B dagger B. So this is the Hamiltonian of your supersymmetric harmonic oscillator. Okay. Now, since both the operators interact with each other, do not interact with each other, any state, so the state, any questions? So the Fock space or the states in the system are labeled by two numbers. They are labeled by NB, which is the number of bosons, so bosonic occupation number, and NF. So I will represent. So I'll represent a state by NB, NF. So notice that this NB can take any value from 0, 1 up to infinity. But this NF can only take values 0, 1 because for the explanation concept. Okay. So the states of this system are labeled by NB and NF. Okay. Now I define something called supercharge. So supersymmetry is generated by a operator called supercharge Q. So the Q is, if I take this operator A into B dagger. So this is the annihilation operator of the boson. This is the creation operator of fermion. Let's see what it does to a state. So Q, let's say it's acting on NB, and for the moment I'm taking the 0th state of the fermion. So NF is equal to 0. So 0 fermion number state. Because NF can either be 0 or 1. Q, what will it do? Q is basically A, B dagger acting on NB, and NF is equal to 0. Now, B dagger will only act on NF because both the systems are not interacting. So you will have A and B. So B dagger acting on 0 will give you NF equal to 1 state. This was the fermionic harmonic oscillator. B dagger acting on 0 gives you 1. So B dagger acting on, and A acting on NB, see what it gives. A acting on a state n gives you square root of n times n minus 1. It's a loading operator. So you will get square root of nb times nb minus 1, comma n equal to 1. So Q acting on a state. So this state is a bosonic state. Why it's a bosonic state? Because the fermion number nf is 0. So Q acted on a bosonic state, but in the end you got a state with a fermion number 1. So Q acting on a state, Q acting on a bosonic state gave you a fermionic state times some square root of n. This was the definition of a supercharged electron. So it acts on a boson to give a fermion. So Q acted on a boson to give. So now let's see what is Q dagger. Q dagger, if I take dagger of this, basically A, B dagger, dagger. This is B, A dagger. And now let's check what Q dagger gives you. So if you act Q dagger on NB, comma NF is equals to. So okay, I'm giving these as the homework problems. So work these out. So Q dagger acting on NB, NF 0. Then Q dagger acting on NB, NF equal to 1. Q acting on NB, NF equal to 1. And the first case I have already done NB. So try to find this out and see. But so you will see that Q acts on a boson to give fermion, and Q dagger acts on a fermion to give you boson. So Q is basically a supersymmetric. Okay. Now also another thing. Now you had the Hamiltonian H. The Hamiltonian H was A dagger A plus B dagger B. Okay. Now another thing, or other things that you can check are the following. So Hamiltonian H Q, you check this commutator. So this commutator is basically A dagger A plus B dagger B into A B dagger. Notice that here you need to use that A and B dagger, they commute with each other. So this basically is A dagger A, comma A B dagger plus B dagger B, comma A B dagger. And then you compute this. So this is also homework. Okay. Please try to do these, because if you do these algebras, you will get a bit better feeling of what's happening. So check the following commutation relations. So the commutation relations are, again, so the following commutation relations. What you will find is H, Q, and H commutator with Q dagger. Both of them are 0. And then since Q was a fermionic generator, you will compute the anti-commutators. So Q dagger anti-commutator, which is Q dagger plus Q dagger Q. This should give you back the Hamiltonian H. Check these things. And this is basically the supersymmetry algebra. So even if you are working with a quantum field theory system, a supersymmetric system is defined with this algebra. If you have a supersymmetry generator Q, it commutes with the Hamiltonian, and the anti-commutators between Qs gives you the Hamiltonian. So this is the supersymmetry algebra. Notice that Hamiltonian. So please try to do these at home. So the Hamiltonian commutes with supercharge. What does it say? So if two generators commute with each other, what does it say? That you can simultaneously diagonalize those operators, and the eigenvalue of the eigenvalues of those operators do not change. For example, if you had a state psi such that the Hamiltonian acting on the state psi gives you if you had a state psi with energy E, that is H acting on psi gave you energy E of psi. And now if you consider another state, which is Q psi, so this state again will will still be eigenstate of H with same eigenvalue. This is because H and Q commute with each other. Similarly, you can make the same statement about Q dagger acting in the state. Hence, if you had state psi with energy E, then the energy of the state Q psi, so H acting on Q psi, will again be the state E, will again be the energy E acting. So this state also has the same energy. So what does it say? It basically says that if, let's say, if my psi was a boson, if psi was a boson, then we already checked that Q psi is a fermion. And now if my boson had energy E, then I said that you will have the same a fermion in your system with the same energy E. So this is basically supersymmetry. Supersymmetry says that in a system which has a boson of energy E, you will also have a fermion of the same energy. That is the symmetry of the system. That if you have a energy E boson, you apply the supercharge to get the fermion at the same energy. Okay. Now let me tell about some of the. Okay, let me pause for a second. Any questions?
So, Diksha, just clarify the definition that what you mean by bosonic state and what you mean by fermionic state. I think some of them got a bit confused.
Okay. So bosonic state is a state. Okay, here I have taken NF, and NF will be only 0 and 1 because there is no other quantum number distinguishing them if you have more quantum numbers. So bosonic state is a state which has 0 or even number of NF. So if NF is 2, okay, in the system I have considered NF cannot be 2, NF can be only 0 and 1. But if there was another quantum number labeling a state, then you could have NF is equals to 2, but one is, let's say, spin up, one is spin down, so that both of them are again obeying Pauli exclusion principle. So a bosonic state is basically a state which has either 0 fermion number, so 0 NF, or even number of NFs. And a fermionic state is a state which has odd NF. Okay. So if you have a better way of understanding this is also if you have, let's say, two fermions, psi f1, psi f2 fermionic wave function. If you combine them to say this is chi, then chi behaves as a boson. Why I am saying this? Let's see. This has half integer spin. So n by 2 is its spin. This spin is again some n by 2. The total spin of this combination is integer. So the total spin is integer. So and also if you interchange, if you have a chi which is psi f1, psi f2, and if you have, let's say, chi 1, and if you have a chi 2 which is some other fermion number psi f, some other fermionic state psi f3, psi f4, then chi 1 and chi 2 themselves behave as boson. If you interchange chi 1, chi 2, this you can check. So any state with even number of fermions behave as a bosonic state. This you can check by, yeah. So whenever I'm talking about bosonic state, it either has a fermion number 0 or even number. And whenever I'm talking about fermionic state, it has odd fermion numbers. Okay.
Yeah, so there was another question, that is the Fock space of the supersymmetric harmonic oscillator is simply the tensor product of bosonic harmonic oscillator and fermionic harmonic oscillator.
Yes, complete correct, because both of them are not interacting, so you are just labeling by NB, NF, so it's just the tensor product of the bosonic and the fermionic harmonic oscillators.
Yeah, and the last question, as I can see, is that is this then in your counting system two supersymmetry, n equals two supersymmetry? That's the question.
Oh, n is equals to 2 supersymmetry. Okay. So it again depends on the dimensions. Let me take the simplest case of the quantum mechanics with n equal to 2 supersymmetry. Let's say I have two supercharges Q1 and Q2. So Q1 acting on the boson, I'm calling this as boson 1, will give you some fermion 1. But then you can act Q2 on this fermion 1. Okay, sorry. It depends on real or complex supercharges. So since I was talking about complex supercharges, so you have two supercharges n equal to 2, meaning Q1 and Q2. So you will have Q1 dagger and Q2 dagger as well. Now Q1 acting on a boson 1 will give you a fermion 1. Similarly, Q2 acting on, let's say, boson 1 gives you some other fermion. So fermion 2, F2. And similarly, Q dagger acting on F1 gives you Q1 dagger acting on F1 give you B1, and Q2 dagger acting on F1 gives you some other boson. So you have more number of bosons and fermions because you have more.
So Diksha, just to clarify, so this is basically whether a number is for complex or real, depending on that n equal to n equal 1 depends, right?
Yeah, sorry, I didn't clarify when I said n is equal to 1 and n is equal to 2. The number depends on if you are considering a real supercharge or complex supercharge. So till now, what I have done, I have since I am saying that Q and Q dagger are different because my definition of Q is AB dagger and Q dagger is BA dagger. A and B both are complex. So Q and Q dagger, in my case, whatever I was doing, were complex. So this is also a notation difference. Whenever people refer to as n is equal to 1 supersymmetry, most of them, I think 90% of literature, when they say n equal to 1 supersymmetry, they say one complex supercharge. So if you have one complex supercharge, then you have basically two independent things. One is Q and one is Q dagger. If they say one real supercharge, then only you just have Q. So you just can make from a boson 1 to a fermion 1. So the system you will have is a boson and then a fermion. This will just be the force space. So Q acting on the boson will give you fermion. But then but most of the places where they use n is equal to 1 or n is equal to 2, they assume the supercharge to be complex. Most of the so I till now have assumed it to be complex. So when in my notation n is equal to 2 means you have Q1 which is complex. So Q1 and Q1 dagger are two different things, and then Q2 also complex. Q2 and Q2 dagger are two different things. Okay. Any other questions? Okay. So since I have introduced what is the supersymmetric harmonic oscillator, let's look at some of the properties. So the first property, notice that the Hamiltonian H had A dagger A, which is plus B dagger B, which is basically number of boson plus NF. So this number is always positive, greater than or equal to 0. Because remember, the fermionic harmonic oscillator had minus half and the bosonic had plus half. This minus and plus half cancel. So so this is a property in general. A supersymmetric system has energy always greater than or equal to 0. Okay. Another way to see this is because Q dagger is a Hamiltonian. So it's basically like a square of an operator. So Hamiltonian is a square of an operator, and the square of an operator should be positive. So and this property is very useful actually, because in a lot of theories, if you have a negative energy state makes your theory unstable. But if you consider supersymmetric system, you always know that the energy will be greater than or equal to 0, so your system will be stable. So that's also one of the reasons of introducing supersymmetry. Okay. Then other thing is Should I talk about the timelines? Okay. Okay. So another thing is that the ground state. So the ground state. So the ground state of the system is what? NB is equals to 0, NF is equals to 0. So the ground state of the system, of this system, is annihilated by Q. What I mean now, Q acting on NB is equals to 0, NF is equals to 0. Remember here we did Q acting on, where was it? Q acting on this will give you square root of NB minus 1, NF equal to 1. But since NB is 0, Q acting on this state will give me 0. From here, from square root of NB you will get 0. So Q acting on this will give you 0. So the ground state is annihilated by supercharge. Another thing is that the energy of the ground state. So energy of a state is now NB plus NF. So if NB and NF are 0, so the energy of the ground state, so the ground state energy is always 0. Notice that these two properties will change if supersymmetry is spontaneously broken in your system. Since I'm almost I'm running out of time, I will talk about what is spontaneous breaking of supersymmetry and how can you tell, can you define a quantity which can tell you whether the supersymmetry is spontaneously broken or not. I'll talk about this in the next lecture. I think that, yeah, that's it. So for today, I think that's. Please try to do these homework problems, because once you do these Suzie algebras, you will get a more feeling of what it. So this is one of the most important things you should know. This is the supersymmetry algebra, and we will use this algebra as the defining, as a definition of a supersymmetry system in coming lectures. Okay, I think I'm done.
Okay, so now any of you can unmute yourself and ask questions one at a time if you have.
Sorry, so I am still not clear regarding the number, how the number of n is being defined, because right now in the non-interacting case, we have AB dagger is equal to B dagger A. So in principle, both of them are the same operator Q. Is it the supercharged Q? But in the interacting case, these two would have been two different. B dagger A would not be equal to AB dagger, right? Or by interaction, you mean there is no extra term in the Hamiltonian, which is a 3-order term or 4-order term?
No, wait, but even here, AB dagger is not equal to B dagger A.
Sorry, Diksha, you mean BA dagger, right?
So the BA dagger.
Yeah. Okay.
Even here, Q and Q dagger are different operators.
No, I'm talking about AB dagger and B dagger A. So my supercharge would have been AB dagger or B dagger A. When these two are different, then I would have a n equal to 2 supersymmetry.
Yeah. So whenever you count what is the supersymmetry, you count the number of independent supersymmetry generators. So here I had taken a very simple Hamiltonian. Hence, these two things which you are saying were same. So I was saying it as n equal to 1 supersymmetry. But in the case, the complicated Hamiltonian, you always count the number of independent supersymmetry generators.
Okay.
And that's why also the dimension of the system is also important, because number of independent components of a fermion depend on which dimensions you are working in. So for example, if you know a Dirac spinner, in 4-dimension Dirac spinner has 4 independent components. Yeah. But in 2 dimensions, it has only 2 independent components. So yeah, so you usually talk about the number of independent components when you talk about the number of supersymmetry in your system.
Thank you.
Other questions?
There is a question in the chat, connection of supercharge with Noether theorem. So yeah, so if you write down the Lagrangian of the system, I had written down the Hamiltonian. So if you write down the Lagrangian and then you write down the Suzie variations. So the supersymmetry variation, I was not sure whether I should cover that in the lectures or not. So maybe the last 2 lectures I will focus on the Lagrangian formalism. So I will write down the Lagrangian. I will write down what is the supersymmetry variations. So, and given the supersymmetry variations, you can compute the Noether charge, and it turns out that the Noether charge is the supercharge. So there's something. Are negative energy states useful in the scenarios like cosmology? Would supersymmetry be irrelevant there? So it's one of the bad things about supersymmetry, that you cannot have de Sitter vacuum if you have a supersymmetry system, because of basically negative energy. Yeah. So
But the supersymmetry can be broken, no, spontaneously, and then
supersymmetry can be spontaneously broken. And yes, I will talk about the how can you check whether the supersymmetry is spontaneously broken or not by defining a quantity called Witten index. I'll talk about it tomorrow in the next lecture.
Diksha, can you send the PDF file of today's talk?
Yes.
Okay.
I don't know if my handwriting was okay, or if I should write down again. I can send.
No.
It's not
whatever
okay.
you wrote, just send that. You don't have to write separately. I mean, whatever you wrote.
Yeah, I'm asking whatever you have written down on the pad.
Okay.
Maybe one last thing I request you is that maybe you can just mention about this pairing of states and unpaired ground state, just to give the contrast, and then we can end.
Yeah, I wanted to talk about it when I introduced Witten index, but okay.
Okay, that's fine. Okay.
Not because then I can also say how is supersymmetry.
Yes, you can compute the Witten index. Okay,
Yeah.
yes, that's true.
Okay.
Any other question?
There are some things in the chat which I can see only now. But
Yeah, I was trying to answer on the go.
Okay.
Okay, maybe one thing is that maybe you go and Diksha send us the material. So so Mukta or I will send you the PDF, and
Yes.
maybe before next lecture, which is on Wednesday.
Wednesday.
Yes, before that you can have question, you can ask, and then we can start. That's also fine.
Or no, on 6th from 3 o'clock there is Rajesh's talk also. So maybe we can just plan it properly.
Rajesh is speaking on that day on ICTS?
On 6th, yes. I just got an email today.
Okay, so let's discuss it, and then I'll discuss with Diksha, and then we can send the final.
Which
Yes. Gopakumar.
He's speaking, okay.
Yeah.
Anyway, I have a Senate meeting on 6, so don't put anything on 6.
We can do it tomorrow also.
Tomorrow is fine. Tomorrow is not day.
Maybe.
Tomorrow is fine for me.
Tomorrow is fine with me also.
No, but just a second. For the students, if they want to go through it, and I'm sure they will go through it, many of them, then probably they need some time, right?
Yeah. Okay.
But Navamita, the 6th is okay. We can stop the recording. But Navamita, the 6th is also bad for 4th year, because they're coming out and many of them have to change hostels.
Okay.